Yeah, we are live now.
As a convener of ICDAMS2020, I welcome Dr. Weiping Wu, George Daniels Lecturer, University London, to deliver the keynote address. Welcome you, sir. Now I request Dr. Deepak, Associate Dean, International Affairs, SSC SIMATS, to give an introduction about keynote speaker.
Yeah, thank you, Dr. Saveetha. Dr. Weiping Yu is the George Daniels Lecturer, University of London, UK. Earlier, he worked as a research fellow in University of Southampton, UK. He also worked as research associate in University of Cambridge. He has received several grants and funding to his credentials. He also received many awards. He is the guest editor of Frontiers of Chemical Science and Engineering. He is the member of RSU. He is a committee member of OSA London chapter. He is chairman of Chinese UK group of SCI. He is committee member of SCI Material Chemistry Group. He is also active peer reviewer of many journals such as Advanced Materials, Advanced Functional Materials, Advanced Optical Materials, and more. He has H index of 31. His paper total citation is greater than 3,900. He has published more than 50 papers in highly reputed journals. He'll be giving his keynote on the topic functional materials for optoelectronic and energy applications. I am very happy to welcome Dr. Weiping Yu once again to address the gathering in our international conference ICDAMS 2020. Over to you, Dr. Weiping.
Working at the City University of London in the UK as the George Daniels Lecturer. I'm the chairman of SCI China UK Group and a senior member of the OSA. So the title of my talk today is Functional Material for Optoelectronic and Energy Applications. So this is a sort of my CDO background. So if you are interested in my paper, you can just search my name and you can find it easily from a City University website or Google Scholar website. So nowadays we are living in a digital world. So we everyone benefit from like a lot from these digital technologies as well as renewable energy technologies. So for example, in daily life, we almost nowadays everyone using smartphones, and we are benefit from the energy savings using LED lights. Then also like electrical scooters, or electrical bicycles, and electrical cars have been developing very rapidly in recent years. And an increasing proportion of energy has been supplied from the wind farm and the solar farms and from the ocean's energy, besides the traditional fossil fuel like coal, petrol, gases. So the world actually is transforming, and these new technology help us to fight against the climate change as well as improving our life and so on. So that's why these optoelectronics and energy are extremely important for the future's development. So let's looking at the electronics market first. So actually, as you can see from the data, in the last 20 years, this electronics market has increased dramatically, and these among them actually these printed electronics is also grow quite dramatically. So why we are developing this printed electronic device or technology? Because the traditional semiconducting technology based on inorganic materials like silicon, gallium nitride, and silicon carbide are very much either expensive or they are very brittle. So they can't be manufactured easily in very large area like beyond say 8-inch. Due to the technology limitations as well as the materials characterization. And the other challenge is it requires a high temperature process, and then it will, and then therefore these facilities to manufacturing these the classical inorganic electronic components are quite expensive. So at the market end, you will feel that a certain device like smarter phones or a laptop are still quite expensive to buy. So also this like a larger screen, OLED or QLED TV, they are on the market, but still they're quite expensive. So therefore, it's very interesting and very important to develop flexible and printed electronics, such as these printed like sensors or displays and photovoltaics and sensors, as well as some wearable textile kind of devices and so on. So then if we review back the development of this type of CPU technology, like the chips, then the Intel Corporation had this roadmap from decades ago, but the recent one was saying predicting that the transistors, the dimension will reduce from 7 nanometer, even towards even smaller, like a 1 nanometer. But it's becomes more and more difficult due to the physical limit and the quantum effects in these devices. So there have been a very active research on carbon nanotubes and a very even smaller or very ultra thin 2D material like graphene, as well as some quantum devices based on inorganic material and nanowires. And then for print electronics, actually, it's highly related to the early years of research back to about 30 years ago. So the Nobel Prize in Chemistry 2000 was awarded to Professor Alan Hager, Professor Alan McDonough, and Professor Hideki Sarakawa. So for their discovery of conducting polymer. So in daily life, we are all using plastic material like bottles or these kitchen foils and so on, and toys so plastic or polymer is amazing material, but they are not conducting. So conducting polymer is very interesting, a very special type of material, and the principle is very much related to the carbon bonds. So there are three classical types of carbon bonds. So if the carbon or molecules or polymer, they are formed by the alternative like a single bonds and a double bond, these bonds can form a conjugated system. So therefore, the electron will subject to a delocalization process, and this will induce a band gap in those material. So once, for instance, if you prepare conducting polymer, semiconducting polymer, actually we will see that it have a very beautiful color, either like the red or orange or blue, this color. So these colors is reflecting of this band gap, very similar to this inorganic material. So similar to the conducting band and this valence band, we call this kind of molecular bands, like as this type of lowest unoccupied molecular option, or this highest occupied molecular option, like LUMO and HOMO respectively. And the energy between these two levels, they are called energy band gap as well. So since I have been working as a master and a PhD student, I've been working on the field effect transistors based on nano and organic material. So then this actually this type of device is essential of this modern electronics. This type of device is composed of several layers. The first layer, semiconducting layer, and the second layer is isolating layer, and the third component are the electrodes in the form in the thin film. And there are other components like substrate and this impact simulation and this connection for these devices. So in my research, I focused very much on these developing materials for organic field effect transistors. And also on developing these organic devices based on new principles, as well as photo detectors based on organic material and organic nanowire transistors. So these materials have been synthesized mainly by these two types of coupling reactions. The first one is called the Suzuki coupling, and the second one is called the Steele coupling. So I was very passionate about chemistry, so I synthesized the various material and purify them. They grow crystals in films, then test their device performance. So then I have developed or proposed a concept of different dimensions of this material. And then among them, there have been linear or one-dimensional semiconducting material, and as well as two-dimensional kind of polymers. So by varying these chemical structures of this one-dimensional material and the two-dimensional polymer, it's a very good wonderful opportunity to turn their optoelectronic property, talking about the conductivity, the mobility, the band gap, and this photoluminescence properties and photovacuum properties. So that's one piece of work then in early years that I have been working on a very special type of material called a TTF, and this TTF will crystal or form very interesting crystalline materials. But however, they tend to be very sensitive. So I proposed and developed a very novel technology by combining this material with polymers, so to form a blend, like a polymer blend as the active channel of this material, to improve the air stability and increase the on-off ratio of the transit device. Then further, then this type of instability can also be solved by chemical kind of design and the synthesis of the material by attaching the electron withdrawn functional groups to the core of the pi conjugated system. So then, besides this conjugated semiconducting polymer, then there are also a wide range of conducting polymer on which I have been working for, as a printable electrodes and transparent conductors like P dot, PANI, and so on. So these polymers can be incorporated with the fused rings for this for the sake of this enhancing the mobility. And at that time, the mobility of this polymeric material was quite low. And I introduced this kind of firstly the high conjugated like building blocks, as well as this donor acceptor, like this type of structure of these polymers. Then successfully increased the mobility. And then besides, for small molecules, it's very interesting to grow them into crystals from like you can see the star material for organic transition independence. So this crystal will show better performance. But at the same time, during this growth, the material will form this kind of merged structure, so that this benzene rings will be able to react with each other, so they'll form small pieces of graphene structure. So then, after graduating from the Institute of Chemistry, Chinese Sciences, with my PhD, I decided to find a place to do my postdoc work. So then at that time, graphene wasn't so popular. Then I realized that in the literature, saying graphene was a very high mobility material. And therefore, I joined the University of Cambridge, starting working on graphene, as well as other carbon material. So as you can see from this slide, this carbon material can be classified as zero-dimensional, one-dimensional, two-dimensional, and three-dimensional materials. So, and actually, if we think about this various type of very interesting nanotechnology of carbon or nanocarbon material for following, then actually in early years there had been some attention to this kind of carbon cluster material. This is a picture from the University of Bristol, showing the C60, C70, and C1 million. Then the graphene has a similar kind of property. Then I came to England, to the United Kingdom. Is when after my graduation from PhD, I got a postdoc job as a research associate at the University of Cambridge. The building I'm working with is the electrical engineering department or division at the engineering department at West Cambridge. And that's it's kind of a highly interdisciplinary research center on both materials, electronics, and photonics. So the Nobel Prize at the 2010 was awarded to Professor Andrew Game and Professor Konstantin Nozdrov from Manchester University. And their discovery was about the producing or isolating the graphene from graphite using tape technology, and studied a very interesting kind of physics, like device physics and the condensed matter physics on all this type of material. So back to the preparation method, we got a couple methods like simple tape method, like CVD method, and the chemical reaction method, and the silicon carbide route, and so on. So, but they tend to be quite complicated and quite expensive, or the sample size is relatively small, so they can't be produced in larger scale. So in reality, using this method, you really can only get a very tiny amount of graphene, which only allows you to prepare the sample in the lab. So it hints this kind of further development and industrialization of graphene. So therefore, I developed a solution process or liquid phase exploration of graphene. Let's have a comparison with mechanical cleavage using like a very simple technology and tools like graphite and the tape. Then actually what you can get using very simple process is you can get very small area of graphene. Probably, although the quality is quite high, but the size or dimension is usually in the tens or hundreds micron. So you can only find them on the microscope. But these samples are quite nice for fabricating high performance devices. But this process is not controllable, so you can't really get it very high quality, very large area uniform graphene material. So they're having efforts on growth graphene on this wafer at the wafer scale. This slide showing the facility developed by the company Axtron that work closely with Cambridge University. And then also the Samsung and so these companies are working from very early years on this CVD graphene, and the scale up very dramatically towards 30-inch. And then this process needs like a transfer of this graphene electrodes from the copper, which serves as a catalysis. So therefore, still we can't see a lot of kind of practical use even using CVD graphene. There are some demos from Samsung, like for touch screens or maybe for OLED electrodes, but still, I think this process is quite expensive and it might be very challenging to get like a flexible electrodes at a low cost. So there's another kind of method that many researchers have been involved on using graphene oxide, which is a low-cost material by chemical chemical synthesis procedure. So what you are doing actually here is you can integrate this kind of acid molecule in between this layer of graphene of this graphite lattice. Then this acid will react with a crystalline, like a plane or crystalline domains of this graphene. So therefore, to induce these chemical function groups as well as defects. So therefore, this graphene or GO, graphene oxide or GO, even after reduction, then it contains a high level of this type of defects. So we actually could not get very satisfied, a very high, excellent performance of graphene thin film. The sheet resistance is about 1 kilo or a few kilo ohms per square, 70%, 80% transparency. So then there are other kind of thin film fabrication methods like spin coating, spread coating, roll coating, and so on. So you have advantages over the thermal evaporation on low cost and a large area. But the central thing for the core thing for this type of process is the ink actually. So back to this slide, so by liquid phase exploration, then I focus on developing or producing the inks at a low cost from graphite using very simple process like ultrasonic and centrifuge. So at the time when I came to Cambridge, in the lab, then only a very small volume of ink can be produced. Then gradually I scaled up the ink, and the ink has been scaled up to the liter scale, even ton scale. So using this process, this graphene can be produced at a very low cost, but in high quality. So this graphene lattice, unlike GO, then contains nearly zero defects, and through the Raman, then we can see that this deep, even though got deep peaks, but they are from the ages of the graphene. It's not like structural defects. So therefore, using this ink, I inject printed these inks on the substrate and get this like this thin film or for the device application. Then even that this printing process for polymeric material or for organic material, they have been very well developed. But for graphene, due to its very unique, like a chemical or physical property, like the very low surface area, it's very it's a low surface energy, so it's very difficult to deposit this kind of material or ink onto this substrate. Then it's essential to functionalize the surface to get a very specialized like ink or get a continuous film. So then also another challenge of using graphene for transistor device is it has zero band gap, so we can't get in high off ratio of this using zero band gap graphene as active material channel material. Then by hybriding with a semiconducting polysilicon material PQT12, then I managed to improve this off ratio significantly while maintain a high level of this mobility. And this paper has been published at ACS Nano, and the citation so far is more than 900. So this is like compares the state of the printing technology, and then our results showing that this is a really big step and like a breakthrough in this inkjet printing and graphene transistor device technology. And after the paper was published, then there have been a lot of kind of scientific media that reported my results, and I'm really proud of this kind of this work. Then next, I will move to the carbon material for energy applications. So the carbon material can be used for a range of energy devices like supercapacitor batteries and smart windows. So firstly, I will introduce about the energy management. So now there's a lot of glass buildings, but in summer we are suffering a lot from this high temperature in the room, and so therefore we can design some smart window to manage this solar energy, so that you can feel cool at the summer and feel warm in winter. So using the solution process using graphene decorate with a silver nanoparticle to enhance electrical conductivity, and coated by a roll process, and successfully produced a very large area transparent conductors. By sandwiching this like a liquid crystal dispersed in polymer, also called PDLC, with this transparent electrical graphene. So I successfully demonstrated this smart window device, which was shown at the Royal Society exhibition in 2011. Then also this flexible graphene electrodes were tested by this bending test, and then as comparing with indium tin oxide, which is an organic transparent conductor, this graphene electrodes only increased the resistance 10%, while this in ITO increased their resistance 350 times. So then this next slide shows the next part is about the energy harvest using carbon material. So again, still the solar is, everyone knows that the solar is a renewable or clean and free energy, free energy source. So you don't need to pay for solar or enjoying the sunshine, dry your clothes or dry food, and so on, you're eating free solar energy. Then the solar energy has a massive or almost unlimited supply of got to this amount, and it doesn't include any pollution and or any carbon dioxide emission. So therefore, it's really an ideal energy source. However, the solar energy has several major kind of challenges. The first challenge is relatively low density for the solar energy. So it's only about 1 kilowatt per square meter. So the second challenge is the solar energy is not distributed only at the visible or UV region, but about more than 40% or more than 50% of the energy is distributed in the form or in invisible light, in the invisible infrared light. So therefore, it's still challenging to harvest the light using traditional nanomaterial, because usually semiconducting nanomaterial has certain band gap, so you can't kind of cover the whole range of the spectrum or solar spectrum. So carbon instead is a very interesting and ideal material for this type of purposes, because like graphene is a zero band gap material, which means that you can harvest the energy broadband and so on. So then, then using this this type of principle, it's possible to build a solar energy harvest device to stimulate the water to generate steam from seawater or from polluted water, and to get drinkable water. Towards this end, then there are two major challenges. The first challenge is that this generation steam rate nowadays has reached very much very close to the theoretical limit. It's about 1.5 kilogram per meter per hour on the one sun. And the most reported material has been used are either like a gold nanoparticle or carbon nanotube or other materials. They are quite expensive or unstable, or they're not environmentally friendly. So therefore, I propose that using the biomass straw to derive the carbon material as this kind of active material for solar energy harvest application. So this material has surface area and have proper pore size. So therefore, in addition, they got excellent mechanical properties. So it's not like just a powder. You got a kind of a bulk or kind of very low density, like a brick. So it's very lightweight, but it looks like a kind of small pieces of this type of like a brick shape. So it allows us to construct or build this kind of solar steam generation plants or devices. So in this work, then this type of biomass material are combined with the geopolymer material for the solar steam generation purposes to obtain seawater. And by introducing the wind energy besides the solar energy, I managed to boost the performance about 5 times. So then this work has been published at a decent journal, Advanced Functional Material, as a front cover in 2018. So following this work, then I further synthesized this carbon material from the plastic, from the particular plastic, PVC, which contains a chlorine atom, for the consideration of reducing the pollution and protecting the environment. So by very simple, very low cost KOH treatment, so this chlorine item can be knocked off and to release discharged as HCl or NaCl or KCl in this process, and this carbon material can be obtained at high atomic content, and then got a very ideal solar absorption spectrum. So then this material showed excellent solar steam generations, as you can see from this figure. Actually, especially at a concentrated solar energy intensity, like 3 sun and 5 sun. This solar energy speed can be boosted. This is because of a very large pore size that allows the efficient mass transfer of this within these materials. So the next slide shows next part is about the carbon material for energy storage. So so during my research, when testing this biomass material, carbon like graphene materials and so on, so I noticed that they're very outstanding or active of this kind of electrochemical performance still in this CV curve. So then when reviewing the topological structures of carbon material, as we can see from 0-dimensional to 3-dimensional, but there have been very little work or attention on how combine these different dimensions of material together. So when I combine this 2D material with 1D material, I proposed a kind of very interesting structure for the electrodes of lithium battery. In this piece of work, I've been using constant sulfide and nanotubes as a one-dimensional material, and graphene as two-dimensional material. So by compositing this two material, then this battery performance showed excellent performance and after 500 cycles. So this work has been published in the journal Nanolater, and then following that, then recently I'm developing some 0-dimensional like carbon material for energy storage. So these carbon hollow spheres have been synthesized by standard template method. So by controlling the fine parameters during this process, then interestingly, from very standard like a sphere structure, I can control the morphology towards this like a ball shaped, nano ball shaped like a carbon hollow structure. So this hollow structure allows me to diffuse this like a material or electrolyte into this inner space of this structure. So therefore, this supercapacitor performance show very interesting like a trend that these materials show the much better kind of supercapacitor performance compared to conventional like a carbon material prepared under the similar condition. So then furthermore, then actually then also I think about the two-dimensional materials. So in this case, then I developed a 0-dimensional plus two-dimensional configuration. So for instance, the MOS2 or WS2 as a semiconductor material, they've been usually used for optoelectronics, but for supercapacitors, it's very difficult to get a very high performance supercapacitor using MOS2 or WS2. So therefore, I synthesized the MOS2 and the WS2 within this type of space of this kind of a carbon spheres and balls. So that then in this case, there are two types of composite material have been synthesized. One is the MOS2 inside this carbon nanoball. And the second type is this MOS2 coated on outside of this carbon nanoball. So then as you can see from the SEM imaging and the TM imaging here, you can see that this material we obtained are exactly the same as the structure we intend to design. So then by comparing the chemistry, energy storage performance, the supercapacitor performance, we actually have made a breakthrough in this area. By considering to achieve the gravimetric capacitance and the volumetric capacitance at the same time. As you can see from the last chart of this slide, so compared to the state of art of this emerging material for supercapacitor, we balance these two performance and reached the one of the best performance among various reported results. And besides this, this kind of cycling stability is still very impressive. So we talked about this. Then this degradation is quite small, like less than 5%. So this paper has been published as the inside cover of the ACS Narrative New Journal at the ACS Applied Nanomaterials. So the final part I want to discuss is about carbon material for energy utilization. So this then this carbon material, then still the dimension combinations, and then the carbon then they can form this composite material. in lots of then I've been talking about the solar energy harvest and electricity energy storage. But when the energy is stored, how we can utilize the energy? So there's a very simple energy utilization is by electrical heating. So using the electrochemistry deposition, then I deposit this graphene from the graphene oxide on this carbon fiber, like this two-dimensional textile, or this. Then I can enhance this type of heating performance, and this type of heating device only allows very low driving voltage from 0.5 volt to 3 volt. So also heating shows very impressive performance. You can see that it's then within a few seconds, within 90 seconds, 120 seconds, we can reach very high temperature around 300 centigrade. And then this kind of heaters can a very ideal source for the solar energy generation, and this device is very radio stable and showing excellent cycling performance. So this paper has been published as the front cover of Advanced Sustainable Systems. So then finally, I would like to make a conclusion on my talk. And then firstly, carbon is a very carbon organic-based material, are excellent multifunction material for optoelectronics, as well as for energy management, energy harvest, energy storage, and energy utilization. So the future of carbon material is that, in my view, is that it will lead to more functional or higher performance functional materials for a wide range of applications within the field of optoelectronics, healthcare, sensors, and energy. This needs effort from the material for devices and the systems. So finally, I would like to thank my collaborators and my supervisors from the University of Cambridge, from Chinese Academic Sciences, from the Shanghai Jiao Tong University. And I would like to thank Professor Bradley, who is my collaborator from the University of Oxford. And I would like to thank the funding support from UKRI, then Innovate UK, then GCRF, the National Science Foundation from China, and the George Daniels Trust, and the International Union of Pure and Applied Chemistry. Thank you very much. That's the end of my talk. I'm very happy to take questions. Thank you.
Yeah, thank you very much, Dr. Weiping. It was really a wonderful talk. You covered all the basics of say graphene, the synthesis of graphene, characterization, and then the results obtained from that. And also you have showed us various applications in energy harvesting, energy management, and even supercapacitor applications, optoelectronic applications, and what are the potential applications the graphene material and its hold, and even the carbon material hold. So thank you very much. Now let me open the forum for question and answer session. So the participants, if you have any queries, you can please ask.
Hello, sir.
Hello, hi.
I'm Sylvester. I have two questions. One is regarding the synthesis. How was it exactly? I know nano core shells we can actually make, but how bowl? That is one question.
Oh, yeah, sure.
Okay,
I will answer this. Yeah, I'll answer this question short very quickly first. So to make a nano ball, you can control, if you check the detail of paper, it's about control the thickness of this precursors for this in the template method. So if it's like a football or a toy, a plastic ball, then if the gas inside the ball is not at a higher pressure, then you can see that it will collapse into this type of ball towards the ball shape. So at nanoscale, it's very similar. So it just control the mechanical property of this kind of shell. Thank you.
Yeah, Mr. Sylvester, you said one more question is there. You want to ask?
Yes, sir. Yes, sir.
Yeah, go ahead.
you have mentioned graphene in the energy management, we can use it as an infrared reflector also. I mean, that is what I perceived from the images that you have shown it.
Yeah, so I think there are several technologies for this solar energy management.
Yeah.
Actually, for graphene, if just put, say, if you have technology putting graphene coating on the window, it's not going to adequate to the management of the energy. So to manage the energy as for the sake of energy saving, you need a more complicated device like a smart window device. Of course,
Okay.
certain simple coating may work, but it's not going to be very high performance energy management system. So another example for graphene energy management is you can using graphene high semiconductivity, but that's a different scenario. But in my example, they are more about managing the spectrum for this solar energy, solar radiation. Thank you.
And this graphene is actually transparent even at infrared, right? I mean, in pure form.
Yes, you are right. So yeah, they're transparent. So they absorb a certain amount. The dispersion curve is quite flat. So that's why I need a liquid crystal like a PDLC.
Yeah. So as such, we cannot use the graphene as the infrared reflector, and you're telling like we have to use some other systems to, I mean, which will benefit in infrared reflection.
Yeah, so for infrared, there are science or nanotechnologies that is so-called metal material when you can design the infrared or electromagnetic like a absorber or reflector. So if it's structured surface, there's a chance that you still can reflect the infrared light at a very high percentage. But but currently the fabrication difficulties only allows it to produce very small area sample. So it's difficult to produce a quite large area, this type of ideal infrared reflectors using just graphene.
So yeah, that's right. And sorry, one more last question. So
Sure.
generally, what is the maximum production by any method? For example, I have come across, by using graphite oxide, and we can make graphene, and even the solar exfoliation also we can make graphene. So, I mean, which is the possible best method? I mean, according to your research experience, what is the best?
I think the ultrasonic or liquid exploration as I presented is quite promising. And of course, graphene oxide is also promising. And in real life, there are companies who invest in this field and can produce graphene at the probably 100 kilogram or ton scale. But another factor, although they make claim even they can produce hundreds of tons per year, the quality of this type of graphene is in question. So it's difficult to get a cheap, high quality graphene at a low quantity and a low cost. There's still challenges. So maybe there will be new methods to produce the graphene.
No. Whenever I'll take graphene from any vendor or something like that, I have to Raman and I have to see the possible D and the G bands. Then only I was able to proceed. So
I think it's a mix of multi-layer, so the quality is in question. So I think it should be quite.
Thank you. Thank you, Mr. Dr. Wu.
Okay, it's my pleasure.
Yeah. Let's take one or two more. Is there any more question from the audience?
Hello, sir.
Yes.
Hello.
This is Bhanupriya, and I have a question. The thing is, we charge our mobile phones for more than 1.5 hours or 2 hours. Is there any way using graphene, that is a semiconductor, so that we can charge within a limited period of time? Have you tried on those things, sir? Or is there any way?
Yeah, sure. So for charging, for faster charging, although nowadays in real life, maybe we talk about charging for much faster than before. It's like an hour also. There are technology not to develop only by battery, but also by electronics. And so for the battery technology, when evaluating the battery material, there are rate performance, which evaluates the charging speed and the stability at a higher density, high current density. So in the lab scale research, I mean, a lot of material showed excellent this type of rate and performance. But when talking about the commercial phone charging or phone battery, it's more about a comprehensive consideration on the capability, the charging speed, and the cost and the safety. So in a word, so there's a technology possibility, but I doubt the over kind of over emphasis like ultra faster graphene graphene based battery technology. So you sometimes you should be a bit careful to identify whether it's a bigger story or fake news from the media, to be honest. So as a researcher or as an engineer, we need to a bit using right language to describe as it's a scientific discovery or it's industry research. So they are very much quite closely related. Sometimes the media, sometimes leading the public, misleading the public. Thank you.
Okay, sir. Thank you, sir.
Thank you. Any more questions? More question from the student. The student asked, what are the measurement techniques carried out for designing a supercapacitor? Like, how you measure the supercapacitor?
Okay, so that's very simple. So there are maybe tens or hundreds, thousands of papers on supercapacitors. So you can see that the majority of the paper will present sets of data. So using this electrochemistry like a workstation, you can get the very basic kind of curves. So it's a collection of different like a curve, like CV curves and so on. Then from the curves, you can extract the parameter. Then I think it's very well established. If you read the paper, and it's not so difficult to measure the supercapacitor performance. So other supercapacitor related performance like cycling and also this type of impedance, like you can also measure with similar setups. But I think besides the measurement, it's a matter of how to analyze data. Thank you.
Okay, thank you. And thank you very much for your wonderful talk. Once again, we thank you wholeheartedly for your time. Now, I'm just transferring to Dr. Shafi sir for his closing remarks.
Thank you.
Yeah, thank you very much, Dr. Weiping. Yeah.
Thank you very much for your attention. Thank you.
Now the 2 days fourth ICDAMS comes to end with a vote of thanks. I wish to express my sincere thanks to our beloved Mrs. Ramya Deepak for her continuous support and advices, which have greatly helped towards the successful organization of 4th International E-Conference on Design, Analysis, Manufacturing and Simulation, ICDAMS 2020. I thank our Principal Sir, VP Sir, PDs of all institute and faculty members of SSV for providing us all possible support towards organizing this conference. I sincerely thank to our chief guest and keynote speaker, Professor Dr. R. Velraj, Institute for Energy Studies, CEG, and INSTI Chennai, for kindly accepting our invitation and gracing the inaugural function. I am also thankful to Professor George Zikeli, Advanced Membrane and Porous Materials Center, King Abdullah University Science and Technology, Kingdom of Saudi Arabia, for accepting our invitation to be a keynote speaker. I am thankful to Dr. Weiping George Daniels Lecturer, University London, for accepting our invitation to be a keynote speaker for the valedictory of ICDAMS 2020. I thank to the organizing team who have greatly helped us in organizing the ICDAMS 2020. I take this opportunity to thank all the national and international advisory committee members, reviewers, chairing the technical committee members. I thank to Dr. Deepak, Associate Dean, International Affairs, who helped us to invite the keynote speakers from abroad. I am thankful to all the participants and students for attending the conference and sure that they have benefited by ICDAMS 2020. Thank you all. Thank you one and all.
Thank you very much. Thank you.
Thank you, sir. Thank you.
Bye.
Thank you.
Thank you, sir.
Bye. Thank you, everyone. Bye.